In this video, we're going to discuss some of the applications of the dot and cross products. The first application regarding the cross product will be about the torque or the moment. We're going to consider the formula for the torque with the symbol tau as the cross product of the vector r, which could be represented as a displacement vector, cross vector F, which is the force applied. Notice that the vector r must start at the center of rotation, positioned at A, and F must start at the end point of vector r. The point of application of F is at the head of the vector r. In order to apply that cross product, we're going to determine the equation in a geometric format, which will be the magnitude of r multiplied by the magnitude of F times the sine of the angle between them multiplied by a unit vector in or out depending on the right-hand rule. We could also find the magnitude of the vector tau. In this case, it'll just be the magnitude of F times R or R times F times sine of the angle theta between them. If you notice, I'm always mentioning theta as the angle between the vector R and F. Therefore, this angle here is not theta that I'm talking about. In this exercise, that would be theta. So in order to solve this exercise and find the magnitude of the torque, we have to do a translation to either the force vector or the r vector. So the diagram will look like this. In this case, theta is represented as the angle between r and F. Given in this exercise that the magnitude of r is 10 centimeters, the magnitude of F is 30 newtons, and the angle theta between the two vectors is 70 degrees. Using the proper approach to the right-hand rule, the index will follow the first vector, which is r. The middle finger will follow the F vector, and as a result, the thumb will flex downwards, showing the direction of the unit vector n. Therefore, if we're determining the vector tau, it will be magnitude of r times magnitude of F times sine of the angle theta times the unit vector n, and it will be in the plane, considering that this direction here is in the plane, and the direction upwards will be out of the plane. So following the formula we wrote, we'll have r has a magnitude of 10 centimeters, but that has to be converted to meters, which will be 0.10 meters. Since the unit of tau is Newton meter or joules, we'll have to comply with the units, times the magnitude of F, which is 30 newtons, times sine of 70 degrees, n unit vector in. And therefore the magnitude of that tau will be simply 0.10 times 30 times sine of 70 degrees. Therefore the answer is, or the magnitude of the torque here, or the moment, will be 2.819 joules or Newton meters. As for projection of a vector in 3 space, it's exactly the same approach to it in terms of projection of a vector in 2 space. I'm going to show 3 cases. Case 1, where the drawing is shown here, case 2 here, and case 3 in here. The way we would do projection, In order to do the projection, we'll always draw the shadow of the vector we want to project, orthogonally drawn onto the other vector, and therefore that is the shadow of vector B, and that is the projection of B onto A. Similarly here, we notice that the vector B is longer or bigger in terms of magnitude than vector A. In order to do this projection, we would extend the vector A. We're interested in its direction. And again, that shadow is going to have to be, imagine there is a light here, light source, and the shadow has to be dropped orthogonally, or the projection is orthogonal and the shadow is formed. And that would be the vector projection of B onto A. Similarly here, we're going to extend vector A backwards. And again, imagine there's a light source. Orthogonal projection is going to be down onto vector A, and that would be the vector projection B onto A. In terms of the formula, it's exactly the same. So the projection of vector B onto A as a magnitude, it is the absolute value of vector A dot vector B over the magnitude of vector A. That would be the magnitude of that projection vector. If we're interested in the projection vector itself, we need a direction. So we're going to write the formula now without an absolute value, because we're interested in that negative sign to show in case the projection is in the opposite vector or opposite direction to vector A, like in case 3. And then we need to multiply it by the unit vector of A just to give it the direction. So now we have a magnitude and a direction. We'll also be interested in writing it in an algebraic form. So we could extend and represent the unit vector A with its formula. So A dot B over magnitude of A times the vector A divided by its magnitude, which will yield A dot B over the magnitude of A squared times the vector A. So these formulas we've seen before. The application is exactly the same as the work we've done before. As for calculating work, again, the approach is exactly the same. Work is the force vector dot the displacement vector, and we will use the dot product application here times cosine theta. So the magnitude of the force times the magnitude of the displacement times cosine of the angle theta between them. And we've seen previous applications to that. Another application for the cross product is the ability to calculate the magnitude of an area, as we will see on the diagram to the right. And the area will have the formula of the magnitude of A vector cross B vector. And I'm going to show why this would be true. So we all know that a parallelogram's area is the technically length by the height, and we would do it normally by L times H, given that this side is L and obviously the H is here. So if we look at the cross product, we know the formula now, which is the magnitude of A times the magnitude of B times the sine of the angle between them. But if we rearrange it to write the magnitude of B times the magnitude of A times sine of the angle between them, we will quickly notice that the height divided by the magnitude of A is sine theta. Therefore, the height is equal to the magnitude of A times sine theta. As a result, vector B is the length, and H is A magnitude times sine theta. That gives us the area to be the absolute value of vector A cross vector B. In a similar approach, we're going to show that the volume of the parallelepiped that is formed by the vectors A, B, and C is given by the magnitude of the triple scalar product. We could do A dot B cross C. And the reason why I did A dot B cross C, it's simply because B cross C will give me the area of that volume. And when I do a dot product with the A, I get the height, and therefore I'm having the area of the base multiplied by the height, and I get the volume. So we know that the volume of a regular shaped prism is the area of the base times the height. So here I could see that the area of the base is the magnitude, as shown before, of the vector B cross vector C, and I want to multiply it by the height, which is a magnitude, and I've shown it before as well, that it is the A cosine theta in this case. So we need to multiply, instead of H, by the magnitude of A, which is absolute A, times the cosine of the angle alpha shown above. So alpha is the angle between the vectors or the sides of magnitude A and the height H. And if we see all that expression, it's nothing but magnitude of vector A times the magnitude of the cross product times the cosine of the angle alpha, which is the angle between, technically, the cross product and the vector A. So the reason why I'm interested in that alpha, since the cross product's vector is perpendicular to BC's area, therefore the angle between the actual height and A is that alpha I'm looking for. If we see this as a scalar quantity, therefore it is the magnitude of A dot B cross C. And that is what we call the triple scalar product. And it also helps to prove if the three vectors are coplanar. If the volume is 0, then all three vectors belong to the same plane. They don't create a volume. And if that triple scalar product is any value different from 0, then therefore these vectors are not coplanar. That is the end of the lesson, and see you in class.